Hello, everyone. My name is Nicholas Maneri. This is Team Two's senior design project, our final demo. We're talking about our water treatment and cybersecurity project. Our goal was to create a cyber-aware water treatment system that automatically adjusts the pH of water to drinkable levels by April 18, 2025 for less than $1,000. This is our team. We were 8 people total. We have 2 computer engineers and 6 electrical engineers. And from left to right, there's Nick Maneri, Josh Weathers, Zach Santarelli, Evan Link, Todd Funk, Jamin Anthony, and then Diana and Angelica Maslinchuk. Our objectives and motivation for this project was to create an automated water treatment system that would take in dirty and acidic water, move it through the system that will purify and neutralize it. We use GE's Mark 6E system that will automatically automate water sensors, pH monitoring, and pump control. We developed HMI using Simplicity software that will show system functions and created logic using Toolbox ST software that will control system functions.
Hello, everybody. My name is Todd Funk. I'll be talking about the project goals and deliverables. For the prototype demonstration, we wanted to show automatic flow from tank 1 to tank 3 with pH checking in tank 2, as well as a cybersecurity abnormality check. We also have a HDMI display that will show which sensors and pumps are active, HMI on and off switch to kill the processes as well. It also alerts the user when there is the cyber abnormality, as I said. Uh, for cybersecurity, there is encryption, digital signature, and decryption with 3 sets of keys for each tank. There are also communication between each Pi and the Mark 6E controller.
All right, so this is Nick again, and I'm going to be talking about our project implementation. So this is our full system. As you can see, we technically are using 3 tanks, but it's split from 1 fish tank into 3 parts. The system was designed to operate in 3 sections or 3 stages. The first stage, all the way on the left, was the dirty/acidic water that gets poured in, put through filters, which are 5 and 20 mesh, which catch any debris. And then it moves to stage 2, which is the main cleaning stage. And when this tank is full, when the water sensor gets triggered, then baking soda will be dispensed in iterations to neutralize the pH. And then also there's a stir rod that stirs and mixes the water to mix that baking soda efficiently. And then once that's cleaned and neutralized, then it moves to the third tank, which is the clean water and the neutralized water reserve. And then also in between the pumps, there are 50 mesh filters, so to clean the water a little more. This is our emergency stop button. This was wired in series to our pumps. So when this is hit, the pumps will actually turn off, but the system will stay active. It'll just basically pause the system and make it stop working so we can figure out what's going on. Then we have our water sensors. This is placed on the low side of the tank and also in the mid-level. This determines the water level if it's low, high, or full or empty. Then we have our mechanical stir rod. This is a DC motor uh, that's put inside this unit that will help stir the baking soda in the tank. And then we have our baking soda dispenser. There are 6 little units that hold about 2 tablespoons of baking soda each. And then as the water needs to have more baking soda, the DC motor will turn on, pour a little bit more of the baking soda in the tank and then turn off. And then we have our pumps. We're using the SafeFlow 24-volt DC pumps. These just pump the water from one tank to another.
Hello, this is Todd again. This is just the block diagram for our system. Starting on the left with the Raspberry Pi connections, the water sensors and pH sensor will lead to the Raspberry Pi 1. Then leading from the Raspberry Pi 1, there will be digital signature and encryption leading to the Pi 2. Then the data from the Pi 2 will be decrypted and signature verification will occur, which all lead to the controller. Then looking at tank 1 connections, starting from the top, there is the emergency stop. If this button is pressed, it turns off pump 1 and pump 2. Then going down to drop filters, This just catches any of the gunk in the liquid that we pour in the tank, and then finally there are just the water sensors high and low. Moving on to tank 2, there starts with the DC motor contraptions. This just is the contraptions with the baking soda or the baking soda stir contraption. And the only other difference in this tank would be the pH sensor, which just actively measures the pH of the liquid that we have. In tank 3, there are just water sensors and the tank itself. Then finally, all of this leads to the controller and ends on the HMI screen.
Hi, this is Zach Santorelli, and I'm going to do a quick overview of the software design. So for our requirements, we had three main things: the communication, security, and reliability. For communication, the sensor data should be able to be transmitted between the pies separately for each tank. The pies are connected physically using an Ethernet cable, and the system uses TCP sockets to send the data. For the security, the sensor data is encrypted before it is sent to this between pies. The packets are signed using digital signature to verify authenticity, and the system should detect and flag tampering or abnormalities detected between the communication between the controllers and the pies. And then for reliability, the system should be able to handle these abnormal sensor readings and notify the user. And the system should also fail gracefully if there are any issues. This is just a quick software flow chart. Starting at the top, sensor data comes in. It checks if tank 2 is filled. If yes, it turns on the DC motors, which stir and add the baking soda. If not, it just goes straight to the encryption and digital signature step. Then it sends the data to the second pie. And then there, it checks if the signature is correct. If yes, it decrypts it and checks for abnormal states for the sensors. If not, it discards the data. And then the data gets sent to the Mark 6E and the process continues. And then for the software theory, on the two Raspberry Pis, we have two main functions. For the first Pi is ComPi1. Collects the real-time sensor data from the pH and water level sensors. It encrypts the data using RSA, which is asymmetric encryption, which uses two keys. It sends the encrypted data and digital signature via TCP sockets to the second Raspberry Pi, which is located next to the Mark 6E controller, and it also drives the mechanical stir and baking soda dispenser DC motors. For ComPi2, which is the program running on the second Pi, that receives the encrypted data and validates the authenticity of that data using the signatures, and then it decrypts the data, checks for abnormalities, and then verify or notifies the user if there are any, and then finally distributes that data to the Mark 6E for use in its logic.
So now I'm going to show the implementation of the actual system. So first the water gets poured in. You can't really see in the video, but the bottom sensor gets triggered. And then the second bit of water gets poured in right until the top sensor gets triggered. And that signals the system to start pumping into tank 2. If you can see with the mouse, he's selecting the HMI button, which turns off the HMI screen and kind of pauses that stuff where it's at. But that turns back on. And then the tank's now pumping into, or the pump is now pumping into tank 2 until the top sensor gets triggered. And it does. So now the stir rod starts stirring and the baking soda pours a little bit out into the water. And if you see on the HMI screen on the left, you can see the pH starting to climb. That's just because the pH is being mixed, or the baking soda is being mixed in the water. And that'll keep going until the pH is at a good amount, which our level limit is 6.5. So baking soda will keep getting dumped in and mixed until that is at the limit. And so we're reaching that limit now. And so we just reached 6 or 6.5, and now uh, the system will say, hey, time to pump into the next tank. And then for demonstration purposes, we hit the emergency stop button, which pauses the pumps from moving, and then turning it back on just resumes them. And now in the last tank, there's clean water and neutralized water. So that pumps up until the high level sensor is triggered. And just like that, the system will stop.
This is a quick demonstration of the cybersecurity. So there's an abnormal state where two separate low sensors are active at the same time, and then the Pi shows that on the screen.
Here is just a quick sped up recording of our HMI. As you can see, there are 3 tanks. On each tank, there is a low and high sensor indicating low water and high water. In tank 1, once the high is reached, the pump 1 status will go off, indicating that pump 1 is now transferring water. Once the high in tank 2 is reached, the status for pump 1 will go off. And then in top right, once the pH is between 6.5 and 8.5, pump 2 will start transferring water and the status will go off. And finally, once the high water sensor in tank 3 goes off, the pump 2 status will go off and the request status for pump 3 will go off. Now in the bottom left, the duct, if 2 high water sensors go off at the same time, it'll say abnormally detected and to refer to the Pi, as well as to press the e-stop. Then if you go to the little switch where I just pointed my finger and you switch it, it'll show that the pumps are off, meaning that no more water will be transferring.
Hello, I'm Evan Link, and I'll be first discussing the discussion of the results. The first thing I want to bring up is the successful integration of the Mark 6E controller. We were able to accurately integrate the controller and effectively utilize and manage the water treatment process. The logic was designed and implemented using the Simplicity software, and it was reliable and it worked very well. Accurate water level detection. The water sensors were installed at the bottom and the middle of the tank, and the integration of these allowed us to provide accurate detection of each water in the tank, of the water level in each tank, and this enabled us to allow the automation process to work effectively. The automated pH monitoring and the adjustment system is done with the pH sensor and the baking soda dispenser. And this system allowed us to manage the pH of the water in the second tank, allowing us to then transfer it to the third tank where it was neutralized and clean. And the reliable water transfer between the stages was done with the motors, which are the pumps. And then the real-time system monitoring was done with the human-machine interface, which was also built in Simplicity. And this displayed real-time system status and included tank levels, pH readings, pump statuses, and alarm conditions. This allowed us to improve usability and situational awareness. Moving on to the challenges and bottlenecks. Some of the issues we had were that the pump wiring connection issues, that the repositioning of the pumps, and during the assembly and disassembly of cleaning the tanks and various other things caused us to have some wires come unplugged or misplaced. We also had issues with the controller access delays. Sometimes other teams would be checking them out or using them at the same time as us, and this caused them to be slower or sometimes even completely locked out of the entire system, where we'd have to message them directly and resolve this. Raspberry Pi issues. The Raspberry Pis got corrupted sometimes, and we quickly learned to back up our code so that we were able to pick up where we left off last. The 3D printing adjustments. Multiple iterations were having to be done of 3D printed components because the dimensions would be off, or there would be tolerances in the printing methods. And then last but not least, the chemical dosing calibration. We actually had issues with the pH sensor where it would be shown too much of an acidic compound for too long, and this would cause it to have almost corruption, or if it wasn't cleaned correctly, it was very finicky and it was sensitive, and then it would have issues. The conclusions I will be bringing up next are that we were able to successfully build and automate a water treatment system that filters, balances acidic water, and we use the Mark 6E controller with Simplicity software to manage logic and pH control, integrating this together with Raspberry Pis, relays, automated pumps based on water level positions. We were able to overcome issues like wiring errors, sensor misalignment through modeling updates, chemical dosing accuracy, team collaboration. All main features, filtration, pH monitoring, dosing, and water transfer worked as planned. We gained hands-on experience working in integration, coding, wiring, and assembly while doing teamwork and communication skills were getting better. The project met all technical and educational goals. Last but not least, I would like to make some acknowledgments. I would like to thank the Halcombe Department of Electrical Engineering and Computer. Last but not least, I would like to make some acknowledgments. I would like to thank the Halcombe Department of Electrical and Computer Engineering here at Clemson University. I would also like to thank General Electric Vernova for allowing us to collaborate with them this semester on this amazing project and everything they have done for us. Here are our references. Thank you so much and goodbye.